Hi, it is my pleasure to introduce Tandem, or how to secure keys by using a central server while preserving privacy. So my name is Wouter Lux, I'm at EPFL. This has been joint work with Brenda at Philips Research and Greg at the Open University and Radboud University, all of these in the Netherlands, and Camilla Troncoso also at EPFL. So let me introduce to you the main protagonists of today's story. Puppy. Like all of us, Puppy has been hit by quarantine restrictions and therefore has had to find other means to visit Puppy World. In particular, he discovered that he can visit Puppy World online. Now, this sounds great, but he suspects that Puppy World Online is actually being run by evil kittens, and therefore, Puppy has been using all his pets at his disposal, or rather, privacy-enhancing technologies, to access Puppy World Online. Puppy uses the Tor network to have network anonymity, and he uses attribute-based credentials to authenticate anonymously. So from a privacy perspective, Puppy is completely set. However, there are still some worries remaining about security. In particular, the recent attacks on security on personal devices has had Puppy concerned because all these advanced privacy-enhancing technologies and actually many cryptographic protocols rely on the security of a secret key that is being used on these devices. So when an attacker, such as an evil kitten, manages to get access to these devices, they get the key and can do all kinds of malicious things. So of course, Puppy would like to avoid that. So now you might be thinking, but that's not very difficult, right? We just use threshold cryptography. So here is how that would work when you try to secure a key by using threshold cryptography. So threshold cryptography uses a key sharing approach where rather than having one key, the protocol requires multiple keys, all of which need to be present, or at least some threshold majority need to be present in order to run the threshold cryptographic protocol. Now, in the setting that we'll be using in this talk today, we're going to be using one personal device of the user and one central server that we'll be calling the Tandem server for convenience to hold all the secret shares of the other users so that we have secret sharing as a service. Now, of course, first of all, the user needs to authenticate to the Tandem server so that the Tandem server can find the corresponding key share to use in the threshold cryptographic protocol. We can run this protocol, for example, to create the disclosure proof of an attribute-based credential, and then Puppy can, as before, send this via Tor to Puppy World Online to authenticate and no longer needs to be concerned about evil kitten overlords controlling this. Now, also security seems to be much better. Because even if an attacker gains access to his personal device, that only gets access to one secret share. And even if this device contains a built-in authentication mechanism to the Tandem server, Puppy can always call the Tandem server and say, please don't accept this anymore, and please destroy my secret share, thereby making sure that security of the key as a whole is maintained. So that seems pretty good as well. However, what happens if this Tandem server is controlled by yet another evil kitten? Because this first step of running this threshold cryptographic protocol requires the user to authenticate, there is a time correlation between where the user is authenticated and where the user is anonymous when accessing the service provider that no kind of crypto trickery can actually resolve. Okay, so because the user is authenticated in the first step, any collusion between these two kittens is actually completely going to destroy all the anonymity properties that the pets community has worked so hard to achieve on, for example, attribute-based credentials. So what we would like to do in this talk, and what we would like to do using Tandem, is using the same pattern of using a Tandem server to hold key shares while actually retaining the privacy properties of the underlying protocol that we set out to achieve. Now, Tandem does this using two key ideas. The first key idea is to create one-time use key share tokens that contain an encrypted randomized version of the service key. And we'll be using these to run key sharing protocols without having to identify the user. Now, of course, these tokens don't come out of the blue. They need to be obtained. And what we propose to do is that users either regularly, or the devices rather, regularly obtain these tokens, let's say at the start of the day or throughout the day, so that when these tokens are used, there is actually no time correlation between obtaining these tokens and using these tokens, therefore bringing back anonymity. So let's put these things together and see how that would look. So on the left, we have our favorite puppy with a bunch of key share tokens. On the right, we have the servers controlled by evil kittens. And now we're going to run this protocol. And I want to draw your attention to the little blue bar in the middle. All the communication is going to run through Tor. So first of all, the user's device and the Tandem server are going to run this Tandem Gen Shares protocol that takes as input this key share and key share token, and using this key share token as input, the Tandem server is going to derive a key share. But notice that this key share is actually different from the key share, the blue one at the top, that it has stored originally for puppy. So because this key is randomized, it cannot actually recognize it. Of course, puppy needs to do some randomization on his side as well to make everything still match up. Now they can run this threshold cryptographic protocol, create the disclosure proof, send it to puppy world online, so that even if all the puppies or all the kittens rather on the right collude, nothing bad will happen, because at no point during this entire process is the user identified. So before we go any further, let's make it a little bit more concrete which properties we would like to achieve. So we would like to run threshold cryptographic protocols with this central server while maintaining the following security properties. We would like to retain key security, namely that upon request of the user, any usage of this shared key can be stopped. And because a priori it might not be immediately clear when the user's device has been compromised, we would also like the central server to be able to enforce some rate limiting so that these keys cannot be used too often, even if the user doesn't know. And all of this needs to work against an adversary that can actively corrupt the user's device, can monitor anything that happens on this device, right? So solutions that reconstruct user secrets in memory on a device don't really work so well. And because this Tandem server has, of course, many users, an attacker should also be assumed to be able to control several of them. Now, these security properties only make sense if the Tandem server is honest, but as a side note, I want to point out that because of the properties of the threshold cryptographic protocol itself, as long as the user's device is not compromised, the Tandem server cannot do anything bad. It cannot use the keys because it doesn't have the other key share that is on the user's device. Now, for privacy, we would like to retain the privacy properties of the underlying protocol, even if the Tandem server and the service provider collude. So this means that if, for example, the users of anonymous credential is actually anonymous with respect to the service provider, this anonymity is maintained despite the fact that we use a Tandem server. So Tandem applies to a large class of threshold cryptographic protocols. Unfortunately, it doesn't apply to all of them. What we need is that these protocols, or rather the secret shares, are linearly randomized. So let's see what that means. Here on the left, we have a threshold cryptographic protocol in, let's say, its natural state. The user takes as input the secret share XU. The server on the right takes as input the secret share XS. They feed this into the protocol runs, and out comes a result. For example, a disclosure. On the right, we have a variant of this protocol where we actually linearly randomized the key share. So we subtracted delta from the user share, and then in order to make sure that the sum is still the same, we added delta to the server share. And this is very useful because XS plus delta, at least if delta is large enough, is going to be completely independent of XS. Therefore, hinting a little bit at how we achieve this privacy property. Now, of course, this privacy property we cannot achieve if the auxiliary data that is fed into this protocol by the user is still going to essentially reveal the user's identity. So additionally, we require that this auxiliary data, be it groups to operate on or extra keys, are generic enough that they don't identify the user. Now, for most sigma type zero knowledge proofs, this is all very easy to achieve, but it actually is not the case for all the protocols. So that's something to pay attention to, but more details in the paper about that. So let's have a look at how we actually construct key share tokens. So here on the right, I sketched the setup of these Tandem schemes. So we require an additive homomorphic encryption scheme that I'm denoting by ENC+ and DEC+. And we also use a commitment scheme that I'm just denoting by this little gray box for simplicity. Now, the user and the Tandem server both have a secret share. So the user has XU, the Tandem server has XS, and they'll be using these, or rather randomized versions thereof, in threshold cryptographic protocols. Now, at the end of the setup phase, the user will also have the encryption under this additive homomorphic encryption scheme of the Tandem server key share. And because it also has the public key, it can randomize this encryption, it can add things to the underlying plain text, but it cannot decrypt it, so it cannot actually access XS itself. Now, finally, the user and the Tandem server have a public key that they use for revoking tokens later on, and naturally the user has the secret share a secret key that corresponds to this, but the Tandem server does not. So now let's look at what a key share token looks like. So I'm going to run you through from left to right. So on the left, we have the randomized encryption of the server's key, and you can imagine how you create this. You just pick a delta, you multiply it, you encrypt it, you multiply the ciphertext, and you get the encryption of access plus delta. Great. Now, in order to be able to block these tokens later on, we're going to include the user's public key in this token, and we're going to have some proof for technical reasons that the ciphertext in the first component is actually well formed, and then all of these we put together, we blindly sign by the Tandem server. And now, how would you use this token? Well, you send it to the Tandem server. The Tandem server will check the proofs, check the signature, decrypt this first ciphertext to obtain access plus delta, and then the rest follows. Now, I'm going to show you in the next two slides in a little bit more detail how we construct these tokens and how we use these tokens. But if you're not up for, let's say, a few minutes of crypto, then we'll come back after that with some more easier stuff and conclusions. So here is how to obtain a key share token. So on the left, we have the user. The user has its key share. On the right, we have the Tandem server, also has the key share, everything as on the slide. Now, as the first step, naturally, the user and the Tandem server are going to authenticate. So this part of the protocol is not anonymous. Obtaining key share tokens, as said before, is going to run independent of actually using them, either on a regular basis or at the start of the day. Then the user and the Tandem server are going to run a cut and choose protocol. So the user is going to pick the delta, not very surprising, but it's also going to pick 2K extra randomizers, mu I. That is going to construct the ciphertext C, which is just a randomization of access and delta, so that we get an encryption of access plus delta, and is also going to do the same trick to get encryption of access plus mu I. And it's actually these last ciphertexts that is going to commit to and send to the Tandem server. The Tandem server is then going to ask the user to open half of them, so it's going to pick a random subset of size k. It's going to send that to the user. The user is going to, for each of these ciphertext CI, going to open the commitment and is going to reveal the randomizer mu I that corresponds to it. So the server receives these, and for each of these values is going to check that this commitment indeed opens to CI, and that indeed the decryption of CI equals access plus mu. Then finally, we're left with the commitments to the remaining k value CI. Now, these remaining k value CI, we're going to include in the key share token. So this key share token is not only going to contain the ciphertext C, which is the encryption of access plus delta, and the public key, but it's also going to include these extra values CI. Then the user and the Tandem server are going to run the blind signature protocol on this token. And as part of this protocol, the Tandem server is going to verify that these CIs are indeed as committed before and that the public key corresponds to it. And we'll see on the next slide why this cut and choose proof was actually helpful. So let's do that. So here's the token again. User on the left, Tandem server on the right. And for notational simplicity, I'm not going to show you that this is at a later point in time and via the Tor network, but of course it is. Before using this token, the user is going to compute the differences in the randomization factors between C and CI. So it's going to compute these gammas that are really just the differences between ui and delta, which it can do because it knows these values. And then it's going to take this token, send it to the server, together with the ciphertext contained therein and these differences gamma. It's going to prove that indeed the ciphertexts are in the signature, that this public key is not revoked, in the sense that this token should still be accepted by the Tandem server. The Tandem server is then going to take our primary ciphertext on the left, ciphertext C, is going to decrypt it to obtain a candidate access hat for using data. Of course, the Tandem server is going to check that the signature is valid, that has not been seen before, so that the token can only be used once, that the proof that got sent along is correct, and importantly, that these values CI, when decrypted, do indeed correspond to access hat rather than access tilde, plus the value gamma I. Now, because of this check, we know that from the cut and choose proof on the previous slide, that at least some of these CIs with very high probability are correct randomizations of the user success. And because the user can produce these gammas, these differences between the ciphertext C and the CIs, therefore C itself must also be a proper randomization of access. And this ensures that even though an attacker might be able to control other users and therefore create more tokens, they cannot create more tokens to attack our core puppy later on. So then finally, what is going to happen is that the user and the Tandem server are going to construct these fresh key shares for use in the protocol. So the user is going to take its long-term key share XU, subtract delta, whereas the server is just going to take the access hat that it obtained, take it modulo P, and if you've been following the math along, that should boil down to access plus delta modulo P. Therefore, if you add these two, the deltas cancel out, and this is indeed a proper re-randomization of the secret shares. And therefore, by our linear randomization property of the threshold cryptographic protocol, everything should work out fine. So let's zoom out again a little bit. We're done with all the crypto trickery to see why we achieved the properties that we set out to achieve. So first of all, for key security, we required that it should be able to block key usage and therefore tokens upon request of the user. Now, first of all, the revocation mechanism will ensure that any outstanding tokens that are still in the user's defined and have been used can thereafter not be used anymore. So for revocation, you can just use blacklistable anonymous credentials or accumulators or whatever strikes your fancy. And then additionally, the cut and choose proof ensures that even though the adversary can control other users, it cannot create new users for the user that just requested his tokens. So key security is good. Rate limiting is really much easier. The server just limits how many keys it will generate for that user. And then again, the cut and choose proof will guarantee that an evil attacker cannot generate more. Now, all the proofs of this are in the paper, more definitions, and privacy, which I won't even go into, is defined in the paper. So let's see how well we did performance-wise, because this cut and choose proof might seem a little bit complicated. So we created a C implementation using a fast additive homomorphic encryption scheme proposed by Joao and Nibert. We implemented the BBS plus attribute-based credential scheme, both to create the blind signatures and just to run some more tests using attribute-based credentials, where we used the relic library as the underlying library. And then we did some more computations, and it turns out that if you run this in an online protocol where you can stop attackers from making too many requests, actually a relatively small security parameter of KS20 suffices. But if you want to go the full 128-bit security, you just need to be at KS64, which would be at the right of this graph. But for now, let's focus on what happens around KS20. For KS20, we see that obtaining for the user and obtaining for the server requires around 50 milliseconds. That's fine, that's non-interactive anyway. And then also around 50 milliseconds to actually use it. So that seems pretty good. So just to wrap up, Tandem applies to linearly randomizable threshold cryptographic protocols. thereby enabling the privacy-friendly use of a central server through the use of key share tokens that contain a randomized encrypted version of the server's key share, so that privacy is upheld. And we have cool key blocking and rate limiting properties. We showed through a prototype C implementation that all of this is practical, code is online. And with this, I hope that Puppy can safely visit Puppy World Online despite our evil kitten overlords. Thank you very much.